You've seen this and not believed it. A boat the size of a living room, pushing a ship the size of a skyscraper, not slowly nudging it, actually moving it, turning it, positioning it, threading it through a harbor entrance like it weighs nothing. Your brain says, that's not possible. The tugboat is maybe 500 tons. The ship it's moving, 200,000. That's not a size difference. That's a different category of object entirely. And yet, every single day, in every major port on Earth, this happens hundreds of times. No ship docks without them. No supertanker leaves without them. The entire global shipping industry, which moves 90% of everything you own, depends on this one physics trick working correctly. So what's actually going on? Because the answer isn't the tugboat is just really powerful. That's the wrong question entirely. Let's put this in a different context. You want to move a truck, but you're on a bicycle. Doesn't make sense, right? The truck weighs 20 tons. You weigh 80 kilos. End of conversation. That's exactly how it should work on water, too. A typical harbor tugboat weighs around 500 tons. The container ship next to it, 200,000 tons. That's a ratio of 1 to 400. A chihuahua walking an elephant around the block. And yet, it happens every single day. In Hamburg, Rotterdam, Singapore, hundreds of thousands of times per year. No ship enters a port without tugboat assistance. Here's the wild part. The ship has its own engines, massive engines, but those engines alone can't dock it. Too much momentum, too little control. In a harbor, that's like a freight train with no brakes pulling into a station, so they send in the Chihuahua. And that leads us to the real question, which is far more interesting than how strong is the tugboat. The question is, what does strength have to do with it at all? Let me lock something in before we go further. A tugboat doesn't move a ship because it's stronger. It moves it because a ship on water glides with almost zero friction. And because a tugboat is engineered to concentrate every ounce of its energy into one direction, while the giant next to it simply floats. Force versus mass isn't the game here. The game is eliminate resistance and focus force. That sounds abstract. Let me show you exactly what that means. Here's the first thing that rewires how you see this. A ship on water has almost zero rolling resistance. On land, when you move something heavy, you fight friction the entire way. Rubber on asphalt, weight pressing into the ground pushing back. On water, none of that. The ship floats. Archimedes figured this out 2,000 years ago. The water surface carries the weight completely, and because the ship glides through water rather than rolling over a surface, the resistance at low speeds is laughably small. That sounds like theory, but it's measurable. To nudge a 200,000-ton ship from a dead stop at harbor speeds, the required force is a tiny fraction of the ship's actual weight. The water resistance at low speed is almost negligible compared to what the mass actually is. Compare that to moving 200,000 tons on land. Mathematically impossible for a 500-ton vehicle. The water does the heavy lifting. The tugboat doesn't need to lift the weight. It only needs to overcome water resistance and get the mass moving. That is a fundamentally different problem. But here's the complication. Mass has inertia. The ship doesn't want to move, and once it's moving, it doesn't want to stop. That's Newton's first law, and on a ship without brakes, that's not a thought experiment. A fully loaded supertanker needs up to 8 kilometers to come to a complete stop from full speed. 8 kilometers. The harbor might be 2 kilometers wide. That's the real problem tugboats solve. Not just pulling, control. Precisely correcting, rotating, and slowing an object that naturally resists every directional change. And for that, the tugboat doesn't just need strength. It needs a radically different way of generating force. The Ferrari versus the tractor. Here's the perfect image for this. A Formula 1 car has 1,000 horsepower. An agricultural tractor has maybe 200. Who pulls a stuck truck out of the mud? The tractor, every single time. The difference? Torque. The tractor is optimized to generate maximum pulling force at the lowest possible speed. The Ferrari is optimized to generate speed at high speed. Tugboats are the tractors of the ocean. A typical harbor tug is 30 meters long and hides 2,000 to 4,500 horsepower in its engine room. Those are power ratings you'd find in far larger or faster ships. But the tugboat uses none of that for speed. It converts all of it into pulling force at near zero velocity. The result has a name, bollard pull. Bollard pull is the pulling force a tugboat can exert on a fixed mooring post while completely stationary, measured in metric tons. Picture it. The tugboat is tied to a post on the dock with a steel cable. Engines at full power. How much pull is generated? A typical harbor tug, 40 to 80 tons of bollard pull. That means 40 to 80 tons of sustained, continuous pulling force from a dead stop. For a 200,000-ton ship, you need several tugboats working together. But even that number alone doesn't explain the full picture, because the real trick is inside the propeller itself. Next time you look at a tugboat, look at the propeller. It's sitting inside a metal ring. That looks like a guard. It isn't. It's a weapon. That ring is called a Kort nozzle, named after German engineer Ludwig Kort, who developed the concept in the 1930s. The original motivation was almost accidental. German canal authorities wanted to reduce erosion of canal walls caused by propeller wash. Kort built a ring around the propeller and discovered the boats got faster and pulled more. Why? Put your thumb over a garden hose. The water shoots out faster, not because there's more pressure, but because the same amount of water is forced through a smaller opening. That's exactly what the Kort nozzle does to the water flowing around the propeller. The nozzle concentrates the water the propeller draws in. The pressure inside the nozzle drops. That creates a suction effect. The nozzle itself starts generating thrust on top of the propeller. The result? At bollard pull conditions, exactly when the tugboat needs to perform most, a Kort nozzle generates up to 50% more thrust per unit of power than an open propeller. 50% more. No bigger engine. Just geometry. But that's still not the whole story. Early tugboats had a fundamental limitation. They could pull, they could push, but they couldn't change direction fast. A ship drifting slightly left as it enters a harbor needs a corrective force from the right, immediately, not 30 seconds later after the tug has repositioned itself. The solution: azimuth thrusters. Modern tugboats have propellers that rotate a full 360 degrees around their own axis. No rudder needed. The tugboat can push in any direction without physically turning itself. That makes it something you almost never find in nature. A vessel that can push full force to the left while pointing to the right. Response time: seconds. For a 200,000-ton ship threading through a narrow harbor, that's the difference between a clean arrival and a catastrophe. Imagine you need to open a heavy door. You can push right next to the hinge, or you can push at the far end of the door handle. Same force, completely different result. That's leverage, and tugboats apply it to 200,000-ton ships. A tugboat pushing at a ship's bow can rotate the entire vessel. Not because it's that powerful, but because it's applying force at the end of an extremely long lever. The ship is the lever. The pivot point sits somewhere in the middle. Force at the end creates an enormous rotational moment. That's why docking almost always uses two tugboats, one at the bow, one at the stern. Not just double the force, precise, simultaneous control over both rotation and forward movement. The ship moves because physics allows it when you know exactly where to push. In one of the world's largest ports, Rotterdam, Singapore, Hamburg, ships larger than some city districts arrive daily. Every single one needs tugboats. Not because the captains don't know what they're doing, but because these ships have almost no steering ability at low speeds. The rudder only works with water flowing past it. No flow, no steering. It's like trying to parallel park a car in first gear on an ice rink, and someone taps your bumper from outside to guide you in. The tugboat is that someone. Typical harbor tugboat, 500 tons, 5,000 horsepower, 60 tons of bollard pull. Typical supertanker, 200,000 tons. On water, the tugboat only needs to overcome water resistance, not lift the ship's weight. That's the core of it. Water takes 200,000 tons and makes them nearly weightless in the horizontal plane. No friction problem like on land. No, I need to lift this. Just, which direction should it float? The tugboat provides the answer. The next time you stand at a harbor and watch a tiny boat push a massive ship through the water, you'll know exactly what you're actually looking at. You're seeing Archimedes, you're seeing Bernoulli, you're seeing lever mechanics from high school physics applied in real time to 200,000 tons of steel. You're not seeing a small boat that's stronger than a large ship. You're seeing a small boat that understood the water does most of the work and engineered itself to take full advantage of that fact. Which is honestly the move in any situation where you're outmatched. Don't fight the weight, change the game. What's the biggest ship you've ever seen up close? Drop it in the comments. I'll tell you exactly how many tugboats it needed to dock.